Hello, Algebra 2 students. We're going to warm up by looking at multiplying another pair of complex numbers, and then we're going to divide a pair of complex numbers. And if you haven't already seen that, I'll try to go a little bit slow and break it down one step at a time. Then we're going to look at an example of where complex numbers are necessary in a really basic AC circuit. And if you want another application, there's a great one on Alg2, which is like reflectiveness in outer space. So that video is highly recommended, and this year my class is required to watch it. It's one of their assignments and will be graded. So let's have a look. To multiply one complex number, a plus bi, by another complex number, I think you just distribute, right? You just multiply everything by everything. So it's a pretty simple process. I'll just color code it for your viewing pleasure. So this one is going to be positive 2, right? And this one's going to be negative 8i. So I've hit everything with the negative 2, and I've got to hit everything with the 5i. So I'm going to go those 2 is negative 5i, and those 2 is positive 20i squared. One of the most common mistakes I see when students are working with this and with algebra that looks really like it in future chapters is they forget that I squared. Remember, if you've got an I on one and an I on the other, it's I squared. If you've got an I on one and an I squared on the other, it's I cubed. So just watch out for those. I think it's just a visual thing where they just don't look carefully. So just look carefully, focus those eyes. Hard to watch a YouTube video and do that at the same time. Anyway, yesterday we learned about powers of I. So I squared is in fact what other entity, what other beast, what other animal? It's negative 1. So we can replace this guy with negative 1. You can show that. You can write it down like that. You can write a whole nother step. I'm kind of lazy, so I don't like to do too much. So I'm just going to say negative 1 times 20, right? Because that's times if it's attached, is negative 20. And negative 20 and 2 is 2 minus 20, which is negative 18. If you want to show more steps, if you're prone to making mistakes, then show one more step. I don't care as long as you get the right answer. And then I think we've got some simple like terms right here. In fact, we've got 13 i's and they're all negative. So you can see one complex number times another, and we get one complex number as our result. Okie doke. So what about when we divide two complex numbers? So I'm going to erase that one and get it out of the way. Visually distracted. Yesterday, in my first hour, we learned how to divide complex numbers. So how do you do that, guys? Can you remind me? It's kind of weird. You use a conjugate. So there's that term conjugate. It might appear on your vocab quiz next week. So it's the bottom conjugate. Conjugates are useful in all kinds of different situations. This time, coincidentally, think of it like that. This time, we're going to use the conjugate of the bottom. Other times this year and in the future, you might use the conjugate of a top. Sometimes conjugates will have i's in them. Sometimes they won't. A conjugate is a cancellation device. Let's see what it cancels. Why does that help us if we use the conjugate of the bottom in this case? If we do that, to make this legal, since there's no other side that I can do something to, I've got to go and put it on top as well. So that's really just a specific kind of clever one. The conjugate clever one, in other words. Why do we use the conjugate clever one and not some other one? Because it's a cancellation device. Watch. It's going to cancel just the right stuff on the bottom when you multiply. So if I go like this, I get 4. If I go like this, I get 6i. If I go like this, I get negative 6i. There's the cancellation. It always cancels what are called the cross terms. And the last one, always be careful on the last one. Like I said, it's minus 9i squared. Now on top, I don't know what's going to happen. It's not going to cancel stuff. On the bottom, it's going to cancel stuff. And that's going to accomplish the division. On the top, we just see what happens. So I think we've got 7 and 2 is 14. 7 and 3i is 21i. 8i. What else? 12i squared. Okay, so cancellation accomplished by the conjugate. And the other thing that lets you divide in this scenario is because I squared is negative 1. So instead of negative 9, this is actually positive 9. So positive 9 and 4 is 13. If you want to write that out and say 4 minus 9 times negative 1 and say that's 4 plus 9, fine. But it's getting a little tiresome when we get into algebra at this level to do that. Okay, so on top we've also got not positive 12, but negative 12. So I've got 14 minus 12, which is 2. That takes care of these. And then I've got some other like terms, 21 i's, 8 i's, that's 29 i's. Now that doesn't look quite like one number yet, right? It's not quite a plus bi. So if I rip the common denominator apart, it will be. So I just have to say, hey, that has a denominator of 13, and the imaginary part also has a denominator of 13. Real plus imaginary part, a plus bi. That number results when you divide 7 plus 4i by 2 minus 3i. That's what results. Okay? So, there is another division problem. Let's look at one application. So now I thought we'd look at an application, a physical application. So this one's going to be a little bit involved because I don't know how much you know about circuits at this point, but it turns out that if you're working with AC circuits, so AC is alternating current, that's the current that comes out of the wall. So we're going to visualize a really, really simple AC circuit here. Mostly in my physics class we work with DC circuits. DC circuits are those circuits that are like in your cell phone, anything that has like a battery. So AC and DC circuits are both really common in our modern world. So you want to visualize this AC generator right here basically as the wall. So this is where you're plugging something into the wall. So what have I plugged into the wall basically? This is the circuit that I've plugged into the wall. So where are complex numbers a plus bi going to come into play in this lesson and in this application? Well, here's where they're going to come in. So first I want to talk about what circuit components are being plugged into this wall. So the first thing is, if you have any squiggly lines like this, those are basically just simple resistors. Sometimes resistors are light bulbs. Resistors are pieces of technology. They can be really simple, like just some wires. They can be complex, like light bulbs and things like that, but they basically are just components that heat up when you apply electric current to them. So when we turn on this wall, or this AC generator, we're going to have electrons begin to flow in this circuit. And they're going to pass through these. And as they pass through these resistors, what they're going to do is heat up those resistors. Those resistors are going to resist the flow of electrons. In that process, those electrons will lose some energy. This component right here, if you have a squiggly line, and you probably won't see this in high school too much, depends what you choose to do in the future if you'll see it, this is called an inductor. And I can't talk a huge amount about what an inductor does at this point, because you need a lot more experience with circuits than just electricity and physics. But an inductor basically is something that tries to induce its own current when other currents flow through it, and there's also some magnetic effects. So let's just kind of leave that one a little bit mysteriously for now. This guy we definitely do with DC circuits in my physics classes a lot as well. This is a capacitor. So a capacitor is a common component in just about every piece of electrical technology you can imagine. A capacitor is basically something kind of like a battery. It charges itself up, and once it gets its maximum charge, it would actually stop the electron flow through that branch of the circuit at least. So you can think of it kind of as a sticky surface of Velcro, if you will, and electrons try to go and stick to it. But it's something that charges up over time. The main idea in this application, though, is that all of these components offer resistance to the electrons that are trying to flow through them. So, whether they're resistors, capacitors, or inductors, they try to resist. Resistors, the simplest kind of circuit component, they have a resistance, and that's measured in ohms. That's what this weird Greek omega symbol is. That's the units. So this one we're going to say is 4 ohms. This one's a little bit more resisting the electrons, so it's 7 ohms. These also try to resist the flow of electrons, but they do it in a different way. In fact, they do it in the complex dimension. So these guys have something called, so I'm going to group them together. Instead of resistance, it's pretty similar, but it's called reactance. So that reactance actually lives in the land of I, the land that we have just begun to explore. So you have to consider that resistance to electron flow as a complex and imaginary resistance. So that's called reactance. When you put all of those resistances together, the resistance and the reactance, you get something called impedance. And the overall impedance for a very simple circuit of this variety, where these two branches are in parallel to one another, they, in other words, experience the same amount of voltage from the wall. when you have a parallel construction like that, here's how you calculate the impedance. The overall impedance we're going to call Z, and it's calculated by taking this product on top and this sum on the bottom. So you might be asking yourself, well, Mr. McGee, what the heck? I see only two things here, Z1 and Z2, but I see four things over there. If you're saying that, I understand. What is Z1 and Z2? Well, let me show you. Z1 is going to be this parallel branch's total impedance, which is going to be 4 in the real dimension and 5i in the complex dimension. So that's really just one complex number. So in the second branch of the parallel circuit, we have a resistor and a capacitor. So this guy, just like the other one, is going to provide the real component resisting our electron flow. So second branch, which is what Z2 basically represents here, that complex number is the second branch. The resistance to electron flow will be 7. And capacitors, it turns out, they don't resist, like we just talked about. They react to electron flow when you're trying to stick them in that little capacitor and charge it up. So they actually do that in a negative. So it's kind of like they don't resist, they actually encourage the electrons to flow through them, at least until they're charged up. What I'm really trying to say here is that that also is going to be an imaginary component to the impedance overall, but it's going to be in the reverse direction. Oh, and it's not 4, it's 3. Okay, so you learned a little bit of physics, at least hopefully you learned a little bit about some basic circuit stuff. So now we're going to do the algebra computation. That's just numbers. So the overall impedance for the circuit as a whole is going to be the product of those two parallel branches divided by the sum of those two parallel branches, and we'll see what happens. So on top we're going to have the product, so I'm going to go 4 plus 5i times 7 minus 3i, and on bottom I'm going to take their sum, 4 plus 5i plus 7 minus 3i. And now I basically just have to simplify this down until I get a single complex number describing the overall impedance in two parts, the resistance and the reactance. So let's multiply on top and see what happens. So it looks like I have 4 times 7 is 28, 4 times 3 is 12, it's negative and it has an I, 5i and 7 is 35i, 5i and negative 3i is negative 15i squared. Watch out for those negatives and those I squareds. On the bottom, we just got to put like terms together, so we'll have, what, 11 plus 2i. That's pretty simple, nice. It's very possible you'll get some very large numbers when you're doing these on your assignment. You might get some decimal coefficients in front of I. Don't be scared of those. I know that's definitely going to happen on the fractal problem I assigned. So we remember that I squared is negative 1. So that's going to be plus 15. So what's 28 plus 15? Well, it's 38 plus 5, which is 43. And those are like terms right there. They're both I, so I'm going to have 23i. So there's the top simplified, and on the bottom I've got 11 plus 2i. So are we done at this point? I think the answer is no. That's not a single number describing our circuit as a whole. That's a division problem. So, how do we divide? If you were watching the video a second ago, you should now know how to divide. You should have been exposed to a couple of those problems by now. So you might want to pause it, think about how to do this yourself. Maybe even pause it and finish the division problem and then check yourself. I'll leave that to you. So to divide complex numbers, of course, we multiply by the conjugate of the bottom. So now we've got to do a whole bunch more multiplying. So on the bottom I have 121. Remember, the nice thing about the conjugate in the first place is that it allows the cross terms to go away. In other words, I don't really have to write out 11 times 2i because 11 times minus 2i is going to get rid of it. I do have to write out 11 times 11 and 2i times 2i, which is 4i squared, and I've got a negative there. Okay, on top I might need my calculator, so I'm going to grab it. I'm going to have 43 times 11. 473, and I have 43 times 2, that's not too bad, that's going to be minus 86i, and I have 23 times 11, so I can go to my calculator, that's positive 253i, I'm going to have 23 times 2, which is going to be negative 46 I squared. So let's finish simplifying here. Remember, I squareds are both negative 1, so we'll put a negative 1 in there and there. And I think we'll end up with, I could just write equals up here. I think that'll be okay. So I've got 473 minus a negative is positive, so that's really plus 46. Let me just do that. So that's 519. And I've got 253i minus 86i. So that's 167 i's. And on the bottom, oh, that's negative 1. So it's really just 121 plus 4. So that's 125. I think I'm basically done, except I need to separate this. I need to rip the denominator apart so that I can see the single complex number. In other words, 519 1/25ths and 167 1/25ths I. That represents the overall resistance in the circuit. That represents the overall reactance in the circuit. Together they represent the overall impedance in the circuit. I hope you found this example interesting. If you're in my class this year at least, make sure that you now go and watch the video on albedo. I think it's going to be pretty interesting. It's going to have, of course, a very different formula, but one where you work with putting complex numbers together, and I think it has something to do ultimately with how reflective a certain star or part of the universe is. You'll have to go investigate that one. Make sure you watch it. It is great. See you next time.